University of London, and he is talking about the role of context in human-robot interaction and teleoperation in unstructured environments. And I see the presentation is there, so the floor is yours.
Yeah. Thank you. Thank you for coming. So my name is Arsen. I'm assistant professor in Queen Mary University of London. I used to be here in Cambridge as a Future Roads Fellow, and now I moved on to the new role. So this project was not the mainstream project that I was doing here, for the fellowship. It was like high risk, high return project originally, because we want to kind of disrupt the robot learning in general. So it was on the background, but now it's kind of paying off. So it's a very, very interesting project. So I hope you will understand. If you don't understand, just ask me questions, right? So if somebody tells you that we don't have robots for the road construction, it's lie, right? So we do have robots in every sphere, right? Of our, for example, that machine, right? Very complicated machine, and it's doing it is a robot, right? It's doing very complicated things, right? So we do have robots in our homes, right? But the thing is we don't have uncertainty in those, right? So that one is a well-structured procedure. So it's not a robotics, it's a generally automation, right? So we can automate the processes where we don't expect uncertainties. But when we have uncertainties, for example, a pothole, right? We cannot automate it anymore, right? So we need to do a lot of manual work, and we still do a lot of manual work, right? So that's where uncertainty comes, right? And then that's where the robots right now don't really perform well, right? So uncertainties are really, really bad. And then all the manual works that we are currently doing is all because of the uncertainties, right? And but human and other animals, they are good at uncertainties. But the question is why, right? So here is a bit non-technical thing. Who knows how to skate? Can you raise your hands? Yeah, not many, right? It's not the same thing as walking, right? So we know how to walk, right? But when we change the surface, we suddenly lose our balance and so on, right? So we need to learn it again, right? But the thing is when we learn how to skate, we don't forget how to walk, right? It's not the case in a robot, because robots are focused on one thing, right? And now another example. So here we have rolling. So how many of you know how to roll? Yeah, and it's not so some people who know how to roll don't skate, right? It's kind of closely related things, but not exactly the same, right? But if you want to learn, if you skate and want to learn how to roll, you basically will take less time, right, for you, because there is something correlated, right? So you learn faster. So generally, what we are trying to do, we are trying to bring these things to the robot. So the robot can learn new skills, and the robot can repurpose old skills, so it can learn new skills easier, right? This is what we want to do. Current robotics, they don't really do that because of one big assumption. The assumption is a Markov decision process. It's memoryless. So we kind of have a state transition. So we just have observations, and then based on the current observations, we are trying to estimate what should be the next step, right? And then we can put, for example, additional information to observations, right? For example, okay, the surface should be like that, right? And then we need to put some more information, right? And our input space basically exponentially increasing, right? And it's very difficult to populate the data, and then the space become sparse and so on, right? So this is fundamental difference. And the way how we are trying to solve it by this method called contextual inference, it's a basically new probabilistic model that incorporates the context into the system. It's not like a traditional Markovian one, but with the embedded context. Context here is not what we select. Context is what was learned from the interaction, right? So it's not we don't define it if it is ice or if it is asphalt or anything, right? So it is what learned by the robot from the interaction, and it can be repurposed. So once the robot walks on the asphalt, it can, for example, walk on the concrete and so on, right? It can either repurpose the context or it can create a new context, right? So it's a growing and scalable system. And the important bit of this system is this basically red boxes. So it's about the memory. It is about how it express the memory, how it creates the memory, and how it updates the memory, right? So it's like a growing learning system. It's not like what we tune ourselves, right? So we can basically make our robot work in one setting, and then when we need to update its knowledge, we can update it, right, through this framework. And now, what this presentation is about. This presentation is about the framework that basically I built during the fellowship. So not really good, not very well visible, but it's like a 4 level of abstractions. So you can make a contextual inference at the level of sensory motor control, then at the level of environmental understanding, the way how you understand the environment, communications, and the social presence. Today I will cover like some publications about this like first 3 levels. So to like sensory motor control, we extended architecture called like autoencoder, but we enhanced the autoencoder with the coin model, so with the new representation. So the coin bit is working all the time, and it basically updates its memory and creates, updates, and expresses the memory like the way I was showing, right? The green one. And then we basically process the data and then learn the learning bits, right? Like encoder and decoder and so on. So by using this thing, like we can bit diffusion policy model. Diffusion policy model is basically state-of-the-art model for the robotic control right now, right? So this task was done by the architecture that you were seeing in the previous slide. And the results are like this, right? So we beat diffusion policy method, not by a lot, but still we beat. And what is more important, that the same algorithm works for different tasks. So if, like, for example, diffusion policy model, we need to apply for only one, but this one we can use for a different task because it's switching the context. It understands. Another thing is about the environment. So we did like this work like fairly recently, and then we used it like for the understanding the context about the things that we are interacting with. Like, and then we were trying to solve like a packing problem. For example, when you do packing, like for example, you cannot put the knife next to balloon, right? Because balloon will burst, right? So there's like a common sense that you can put together something that can be put together, right? You can't put the heavy things on top of the, I don't know, like soft things, right? Like you can't put first X and then on top of that, like a bottle of water, right? Like 5 kg or whatever, right? So there is like some common sense, right? And then we were using like the contextual inference for the common sense thing, and then the robot was basically packing. So we were using like traditional algorithm, and then on the background we will kind of make it conditional to the context, right? So where to put what? So, and this is the way how the basically robot was packing the things, right? So it was meaningfully placing them, right? Not, yeah. This is about understanding of the environment, and the third thing is like understanding like is for the communication, like how the robot can understand what the other robot or other person wants to do, right? What is the context? What is currently happening, right, in the system? So generally, it is like a collaborative game. It's called Overcook. So generally, if you want to win, you need to collaborate with your friend, right? So we have like 2 agents, like one you and one is your friend, right? And if you work together, then you can get like a bigger score, right? If you don't work together, then your score will be kind of like lower. And then you can see like we applied the contextual inference, and you can see like our robot like with the green hat is like just staying there, and then when the blue one is like moving around, we can see like how the context is switching. So the robot with the green hat understands what the blue one is doing, right, in the space. And then the same thing, like if you, for example, will block the way, so you surf in this gray area. So if you block it, you can see that the other robot cannot really do anything, right? So then the score is 0, right? And then yeah, so what you have seen is like basically architecture of 3 levels, right? Like in the level of sensory motor control, the first example when you were seeing like the operating the robot when it learns like different tasks with the same model, like in environmental understanding, when you understand the context about the things that you are manipulating, right? And you can basically extend it in time. And then you saw the communication, how the robot can understand each other and each other's intent, right? So what the other robot wants to do, right? And this is like all 4 levels are important for very like unstructured environment that we have in the road construction and stuff, right? So essentially, like by going through these 4 levels, if we will solve them in a certain level, then we can deploy our robots to the road construction and maintenance. This is it. I want to acknowledge all our partners. It was like very good collaboration. Yeah, over these 3 years. Yeah, thank you.
Thank you very much. Very, very interesting.